Okay, so the second topic actually should be with the should be like, oh, I see what was the problem. The second topic should be should be attached with the first topic because it's slightly it's just an extension of the first topic. But with correlation analysis, we are still looking at a relationship between two variables, two or more variables. But this time we are not necessarily looking at causality. Causality is actually saying one thing affects the other. Correlation is saying these things go together. These things go together means if one is displaying in this way, the other one is displaying in that way. What you see with peer friends, right? When you look at friends closely, when one starts buying a Nike and an iPhone, the other one wants to buy a Nike and an iPhone. It means they are correlating. There's a correlationship between them. And why a big point why causality is not necessarily correlation is because sometimes you may have two variables that are behaving in the same way because of a third variable. A third variable is causing two variables to behave in the same way, right? Let's say there is incentive for education. Maybe there's a free scholarship. Then we find that number of students are increasing and number of um, what can I say now? Number of student bank accounts are increasing, right? Now, it does not necessarily mean that because number of students are increasing, number of student bank accounts are increasing. It's not the number of students that is affecting the creation of bank accounts. It could be that it's because the number of scholarships are increasing, then we need more students to get the scholarships, and we also implicitly, because the number of scholarships are increasing, there will be more bank accounts that need to be opened for these students. So if we look at the difference between causality and correlation there, we would see that the number of scholarships increasing has affected the number of students increasing and has created more bank accounts for students. But there's no causality between number of students and number of bank accounts. What you have there is a correlation because now there seems to be a relationship between increase in students and increase in bank accounts because as students are increasing to get this money, they also need bank accounts to be able to use this money effectively. So that's the key thing about correlation, and it may not be as strong a case as causality, but it's also important in descriptive analysis and basic analysis. I think we saw one type of correlation when we were looking at descriptive analysis yesterday, the Pearson correlation. So now we'll be revisiting just some aspects of just to explain it further and see how we can compute it. We have other versions of computing correlations, Spearman, pairwise correlation, Pearson correlation, and so on and so forth. But we'll look at two for this lecture, just to give you a better appreciation of what correlation is all about. So we say correlation is just another way of assessing variables, and it measures the extent of correspondence between the ordering of two random variables. So, and the test, so before doing a correlation analysis, you may not know the relationship between these variables. But once you do them, you can establish that relationship. So, and that relationship only exists when these variables are behaving in a particular manner. So if they are increasing together, that relationship will be positive. If for every increase one is reducing, then that relationship will be negative. And then you have correlation coefficients that will be estimated to measure the magnitude of that relationship. And you can also use scattergrams to demonstrate how these variables relate with one another. So a good example, okay, before we get to the graphs, the Pearson's correlation coefficient is calculated based on this formula. Again, we have seen all of this, right? Summation xy, we have seen how to do it. We know how to do summation x, we know how to do summation y, we know how to do summation x squared, summation x all squared. So all of these are aspects that we have seen. The only difference is in the ordering of this formula. So the Pearson's correlation coefficient can be given as this formula that we have seen on the board. But what we should note is that coefficient should always range between -1 and 1, regardless of the technique that is being used, whether it's Pearson or Spearman or the other ones. Usually, a correlation coefficient ranges between -1 and 1. So if y increases when x is increasing, we say that there's a positive relationship. Positive or direct correlation. Direct also means positive. If y decreases when x increases, or when x increases when y decreases, then we say that they are negatively or inversely correlated, which means one is going in the opposite direction of the other. It doesn't matter. Remember, we have said in correlation is not causality. So if one is going in the opposite direction of the other, then we say they are inversely correlated. So in theory, there are established correlations, right? It is expected that as a country's income increases, as a country's per capita income increases, its poverty level should reduce. But that's not the case everywhere, because there are countries that have as the per capita income is increasing, poverty is also increasing. But of course, that does not mean that the theory is not true. The theory is true for the majority of countries. And that's a case to investigate the relationship of income and poverty in every country, because that the theory says that's the case does not mean it's true. So that's a big point that you can use even in your research to establish a problem statements for an analysis that should be done. You should be able to establish why you're doing a particular study. And if it's a study that has already been done in other places, and maybe the results are contradicting, maybe some have seen a positive relationship between income and poverty, some have seen a negative relationship, then it just further shows that there is need to do it everywhere and be sure whether yours is positive or negative. So the sign of R is always the same as the sign of the gradient or the sign of the slope, which we have seen in causality analysis or OLS estimations as B, which means that if given a relationship or given a table like we have seen, if we get a sign that is positive B, then the correlation will be positive. So the relationship between length and temperature, as we saw in the first table, was positive. It also means that if we compute the correlation for that table, then it will also be positive. And even as I go forward, I should advise that you should use this formula to solve for the correlation for those three tables in the three examples that we have seen in topic 5. Any questions so far? I really hope I'm not fast. I really hope I'm not fast. That I'm going at your pace and that you're understanding. Questions? Should we proceed? Are we there? Should we proceed? Am I talking to myself?
Yes, sir. You can proceed.
Okay. Okay. So So we have established that the coefficients start from -1 to +1. And so there are different qualifications for the coefficients. So when it is 0, we say basically that there's no relationship, there's no correlationship between the two variables. If it is 0.1 or minus 0.1, we say it is very weak or very poor. When it is 0.2 or minus 0.2, it's still very weak or very poor. When it is 0.3 or minus 0.3, it is poor. So right down to when it is 0.9 or minus 0.9, it is very strong. And you may ask why the difference now. So how do we make the difference? The difference will now be in the interpreting the sign, such that if it is minus 0.9, we say there's a negative or there's an inverse and strong correlationship between the two variables. If it is positive 0.9, we'll say there is a positive or direct strong relationship or correlationship between the two variables. Of course, when it's 1, it's perfect. Usually you don't get 1. In fact, where you get 1 is when you test the correlation of a variable with itself. So if you test the coefficient of a variable with itself, if you assume, for example, that y is temperature and x is temperature, and you solve for r, you would see that you would get 1. So 1 is perfect correlation. So the note here says that if we observe that the strength of the relationship between x and y is the same, whether r is equal to 0.85 or minus 0.85, the strength is the same. The difference is in interpreting the sign. So again, here you can interpret based on the 3 S's. The sign, which tells us whether it's negative or positive correlationship. The coefficient or the size, which simply tells us the extent to which the two variables are correlated, and the significance. Again, we have not ventured into significance, but because what we are doing does not give the values for significance. But when we start interpreting the results themselves, we will talk about significance, which is the interpretation of the probability value and the interpretation of the t value or z value. So these are scattergrams that basically show different levels of correlationship. So when r is equal to 1, like we have said, it means it's a perfect correlation. And so the relationship between x and y is perfect and can show that 45-degree line pattern between x and y. When it is minus 0.8, you see the trend is sloping downwards. Not as clear, not slanting the way r is equal to 1 is slanting, but it's more gentle than the normal curve. So if r was equal to minus 0.1, that will be steeper than the minus 0.8 that we have. And when you look at a good example is r 0.6. When r is equal to 0.6, the slope is more gentle than when r is equal to 1. And then, of course, when r is equal to 0, it simply means that there's no relationship. You see the x's are just all over the place. So you can't even draw a straight line. You would even have to draw something like a circle and maybe a what do you call it, moon tiger kind of circle. You draw and keep going around to be able to touch all the x's or to be able to be close to the x's. So there's no relationship between x and y. When r is equal to 0, there's simply a straight flat line, which means no matter the value of x, y does not change. So it's just 0. No matter how x changes, y remains the same. It does not change. When r is equal to 0 is also when you have something like this nonlinear relationship, where it's not always true that an increase in one will lead to the other. So when there's that kind of nonlinear relationship, whether it's a convex or a concave or a quadratic or an exponential, you would have r is equal to 0, because it's simply saying that there exists no correlationship between the two variables. In this case, we are dealing with 2, but you can also look for correlationship between more than 2 variables. Is that clear? Any questions? Okay. Okay. I hope I'm assuming rightly that you are all good. So, examples. 1. The yield of a particular crop on a farm is thought to depend principally on the amount of rainfall in the growing season. The values of the yield y in tons per acre and the rainfall x in centimeters for 7 successive years are given in the table below. So we have rainfall in centimeters ranging from 12.3 to 12. You have yield ranging from 6.25 to 5.68. Of course, it's not in ascending or descending order, so they are you just have figures. Now, the question says calculate the linear correlation coefficient and interpret your results. So again, using the formula, you can look for summation x squared, summation xy, summation y squared, and compute your coefficient of r, which is 0.9807. And so we see that 0.9807 is almost 1. It's almost perfect, which means there's a very strong and direct correlation between x and y. And x in this case is rainfall, y is the yield. So there's a strong relationship, a very strong relationship between the yield and rainfall. And that's what the values give us. Now, causality, I've talked about the relationship between causality and causation. And like I said, causality does not necessarily mean correlation and should not be interpreted as causal. When you're looking for correlation, you should not interpret correlation like you would interpret causality. So this table does not necessarily tell us that rain affects yield or yield affects rainfall, even though we know that according to the theory, rainfall should affect yield. But based on the computation, we are looking at the correlation between the two variables, not one affecting the other. Please don't make that mistake. R is looking at the correlation coefficient between the two variables, rainfall and yield. Co means together. So there's no causality here. So when you're looking for correlation, you're not looking for causality. And I gave you an example of how one variable can cause two variables to have a positive correlation. And another example is this one, where level of income have both higher levels on savings and spending, right? When income increases, savings is increasing and spending is increasing. It does not necessarily mean that spending affects savings or savings affects spending. It only means that because income is increasing, you now have more to save, and at the same time you have more to spend, which means there's a high correlation between saving and spending in this case. But this is influenced by a third factor, which is not one of them. So that's something that we really need to note about causality and correlation. So there's also need to note some of these things about spurious correlation, and then we'll talk about coefficient of determination. But the spurious correlation occurs between two variables that are supposed to be mutually independent. And this is where correlation comes in to be important, because One of the assumptions in the OLS regression is that you should not put two variables that have correlationship in the model. So if, for example, I'm running a model that wants to see how education affects financial inclusion, and then financial inclusion, of course, will be my dependent variable, but the independent variables that I chose are some of the independent variables that I chose are education and literacy rate, maybe school enrollment and literacy rate. Of course, there will be a very strong correlation between school enrollment and literacy rate. So if you include school enrollment and literacy rates in the model, then you would have spurious regression results. So correlation also helps us to guard against such spurious results. Now, the example I've used is very obvious because it's very clear. The value of the literacy rate, what we use to compute the literacy rate, is also school enrollment. So it's very clear that there could be a correlation, but sometimes it's not that clear. So the only way to find out is to look for the correlation itself and check whether there exists correlation between the independent variables that you are using. Another term that is important to note is the coefficient of determination. Now, the coefficient of determination sounds very much like correlation or coefficient of correlation, but it's different because the coefficient of determination measures the R square, and we get the results of the R square when we do a regression analysis. So when we do a regression analysis, the R square helps to tell us by how much the independent variables that we have explain the dependent variable, which means that, like in the example that we have, if we say R square is equal to 0.64, it means that 64% of the dependent variable is explained by the independent variables. Now, remember the analogy I made at the beginning of the lecture between the core factors that affect the dependent variable and the many other factors that could affect the dependent variable. So the question you might have asked is, how do we now draw the line? At what point do we say we have enough variables? What helps us to do that is the R square. So generally, for time series analysis, and I should make this very clear, for time series analysis, you want your R square to be as high as at least 70%, such that you will be sure that the dependent variable is explained by the independent variables to the tone of 70%, which means 70% of the dependent variable is explained by the independent variables. But that's not always the case with cross-sectional analysis. When I say cross-sectional analysis, it means the data varies across cross-sectional units like individuals, firms, farmers, households, and so on. So if you go around with a survey asking people questions or asking firm questions or asking households questions, that is a cross-sectional analysis. So for cross-sectional, R square is not usually a very big deal. But for time series analysis, which is data that varies across time, you see somebody saying my data span is from 1990 to 2025. That's a time series analysis. You want your R square to be at least 70%. It does not need to be up to, when it's also very close to 100, it's a problem. When you have 95% or 90%, there's also a problem there. It means that it's looking very strange. But the higher the R square, the better, but not in all instances. Now, so the relationship, the difference between what we have seen in this course, the correlation coefficient, and the coefficient of determination, is that the correlation coefficient is just talking about the relationship between two variables or more. The coefficient of determination is explaining the extent to which the dependent variable is explained by the independent variable. So just for you to note the difference. And they differ also in the way they are, the connotation. For the correlation coefficient, normally we just write R. For the coefficient of determination, we write R square. So that's the big difference between them. Any questions so far? I can't see the screen right now.
So,
Anybody?
sorry.
Yes, please.
Okay. If you calculate your R squared and then it's at like now 90%, what do you do?
Yeah, it means you should check for things like correlation. You should check for things like whether correlation is a key factor, but you should also check all the other assumptions of the classical linear regression model. You need to check whether there's autocorrelation, whether there's multicollinearity, whether there's no linearity between the models. So, which are I think those are things we have not gotten into, but these are the tests that you need to make to be sure that your results are robust. But that's a good question.
Thank you.
Yeah. So, um, okay. So to wrap up, I think we're left with just one slide. I said this is even shorter than the previous one. So the Spearman's rank correlation is another type of the measurement of correlation, different from the Pearson. The Spearman is a non-parametric method of finding the correlation between two variables. What is non-parametric again? Non-parametric simply means some of the assumptions of the OLS regression may not apply with the Spearman's rank correlation. Most notably, the normal distribution. Remember when we talked about kurtosis and skewness? So the Spearman does not necessarily require that the distribution is normal. So with the Spearman, we can simply just use the formula and calculate the Spearman's rank. But we didn't include the formula here, but just to give you an idea of what the Spearman correlation is all about. So the calculation of the Spearman is carried out based on the following assumptions. One, that the pairs of observations are at least at the order scale of measurements, which means you can order them. You can order the pairs of observations of the variables that you want to estimate. Two, the observations have been sampled from a bivariate population of continuous random variables. So you have data that from the two variables that have been gotten from two populations. And then between those two populations, you now do a random sampling. I think we talked about that cluster sampling. So you first have two clusters, and in those clusters you now do what the random sampling, and then the third one, the distribution needs not be of any specific form, because we have said it's a non-parametric method. You must not use a functional form to specify your relationship between the two variables, which means any two random variables at all, whether they are related or not, according to theory, you can use the Spearman's rank correlation to estimate it. The merits, it does not need too much knowledge about the population. You don't need to know the population because you don't necessarily need to make sure that the sample is a good representation of the population. Again, it's a non-parametric method. Two, this method is very useful in a wide variety of applications, especially when you don't know the population, when you are not sure that the normal distribution is satisfied and all that. So Spearman is like that backup methodology that you may want to use in the case that these assumptions are not met. What are the limitations? One, unlike the Pearson's correlation coefficient, this method does not take into account the values of the observations because it's based on simulations of the two populations that are used, and it's difficult to interpret the data because it's a non-parametric method. So to say, like we have said, as the correlation between A and B is 0.8, is tricky when we come to the Spearman's rank correlation. This method is not very appropriate with too many ties. You see, what makes it is fundamental assumption is also what makes it is also what constitutes its weaknesses. Because the whole idea of having parametric methods is to make sure that we can interpret the data in a way that assumes everybody is inclusive. So, like we do when for causality, for example, we are able to say a unit increase in A leads to in X leads to B increase in Y. And that's because we have been able to make sure that there's normality, there's multicollinearity, there's no multicollinearity, there's no auto, and so on and so forth. But the bigger point here is that it's not the best of methods to use for computing a Spearman's rank, for computing a correlation coefficient. But if all tests show that the assumptions of a parametric method is not met, then this may be a backup plan and justified by the fact that it's a non-parametric method. Yeah, so that's the last slide of the topic. If you're following, can I see your hand? If you have followed through this class, can I see your hand? Okay, thank you. Thank you. I see many hands. Okay, that's good to know. Any questions?
Doc,
Yes?
is this also part of the test?
No, no. I said the test is 1 to 4. The first test is just topics 1 to 4.
Okay.
But before you smile about that, you know, there's the thing with this is that if you just keep it and wait to go back to this only after the test, then you may forget everything. So I still advise that you play around with it even as you're preparing for your test.